Greetings, this is Mr. T. This video is over classification of matter. Now we start to answer the question, what is chemistry? And we give you a little bit more details than we did in the previous chapter. Going to our outline. Chemistry is the study of the composition and interaction of matter. Now often when we look at matter, we're looking at pure substances. Any pure substance is the same composition throughout. There's another definition of pure substance we'll get into. But the best example of a pure substance is going to be good old-fashioned H2O, also known as water. Now, any piece of matter can actually be considered, and usually it has to be a pure substance, but it can be considered a chemical. So think pure substance is a chemical. So water is a chemical. It doesn't have to be something nasty or disease or a carcinogen. So keep that in mind. Chemistry is derived from the word alchemy, which is the study of change. Because when you understand the composition of a substance, then you can actually create interactions and cause changes. So for example, by understanding that water is made up of H2O, I can actually shoot electricity through it, and I can create hydrogen gas, H2, and oxygen gas, the same stuff that we breathe. So now we're going to be investigating a type of matter called pure substances. And this is where we get the term classification of matter, because we're going to break down matter into different categories, starting with pure substances. Now, pure substance is any matter that is the same throughout. So, for example, water is made up of water molecules. We'll get into those definition molecules later on, but it's made up of the same substance throughout. Compare that to something else where you have water, H2O, and then you have spaghetti, such as when you're boiling spaghetti in water. So I'll just have my spaghetti strands. There's my strand of spaghetti, and it's mixed with water. So we call this a mixture, and that's two or more substances that are mixed together. And you can actually use different types of physical processes to separate them out, such as with a strainer. All right. Now, pure substances can be broken down into two other categories, and they can be classified as either an element or elements and compounds. Unfortunately, you can't just look at a pure substance to immediately know whether it's an element or compound. You need to be able to take a look at the particles that make it up. So particles is a generic word. It means things or objects. So for example, we know that water is made up of these water molecule particles. And I'll put those in neat little balls that you can see right there. So we need to investigate these particles in order to figure out whether it's an element or compound. That or just simply memorize from experience whether something is a element or compound. So from experience, you might be able to um, memorize that water is a compound. But now we're going to go into detail about these particles that make it up. So let's take a look at our outline. I have it broken down here for definitions. We just talked about particles. So those are just the generic objects that a pure substance is made up of. And then pure substances. A pure substance is made up of the same particles. So for example, water is made up of the same water particles, H2O, H2O, H2O. Now we're going to go into elements and go into compounds. So in slide 2, we see an example of titanium element and water compound. Again, just by looking at it, you won't know unless you have it memorized whether it's an element or compound. You need to magnify the substances so that you can see it on a microscopic level. So here's water on a macroscopic level, and then here is water on a microscopic level. Now here's the thing. Particles such as water molecules are so small that we don't really know what they look like. We have to use instruments, and they kind of interpret what they look like. So what we like to do is we like to create simplified copies of the actual species, what we call models. So that's a little deep, so let me give you an example. Here is a, let's see, if I were Godzilla, and Godzilla was going to study people, but people are so small, and he were a scientist, but he wanted to study what people look like, he might make a model. And a model of a person might look something like this. So this is a stick model of a person. Now obviously, this isn't what an actual person looks like. There's a lot more details such as hair, muscles, and so forth. But models are simplified copies of some original item. Likewise, we cannot see what a true water molecule looks like, so we make these models, aka simplified copies, of the real thing. And this is one simplified copy that you see right here that I'm circling. We call that a ball and stick model. Here is another example. This right here is a ball and stick model of a water molecule. The stick portion represents something called chemical bonds, which help keeps the individual parts of the particle together. And then the ball represents something called atoms. So this is the smallest building block, and molecules are made up of these small building blocks called atoms, which are represented as balls, and they're connected through chemical bonds, which we represent as stick, which is why we call it a ball and stick model. Now, we can have different types of models showing different aspects of the chemical. For example, the ball and stick model allows you to see these things called chemical bonds, and it also allows you to see the atoms that make up the different parts of the molecule. Space filling model only shows the building block atoms. They do not show any ball and stick. Rather, while the name speaks for itself, it shows you the relative size of each of the atoms that make up the water particles. So different models serve different purposes. But my point is this. It's by looking at a microscopic level through instruments, the individual particles, only then are we able to figure out whether it's an element or compound. So, using our instruments, we figured out that titanium is made up of carbon copies of the same titanium particles you see here that I'm circling. So it's made up of individual atoms repeated over and over and over and over. This introduces one definition for element, and that's where they contain atoms of one type, of the same type. So usually we like to color code these so it makes it a little bit easier. But if you see that they have the same color, then they're going to be the same atom type. So over here, copper is an element because if you were to look at its particles based on the color, they're all the same atom type. And consequently, it's an element. Titanium is made up of all of the same atom type. So therefore, it's an element. The periodic table are made up of letters, and each one or two letters indicates a specific element. And if you were to sit there and shrink yourselves down and look at it on a atomic level, then all the particles that make up the element have the same atom type. So that's why we call it a periodic table of elements. As far as the term periodic, we'll get into that term later on. Now, if this is the same atom type, or one atom type, then compounds are going to be two or more atom types. Now, compounds are actually made up of two or more elements. And so you can just assume that an element is an atom type. An element is an atom type. So let's go through our definition. Here's an element. It's one or more atoms of the same atom type. Whereas a compound is two or more elements. That means atom types. So same atom type for element, two or more atom types for a compound. Another way of thinking of this is if they have different atom types. Different atom types. An element is another word for atom types. I beat that to death. Now let's look at the word S. Sometimes it says the word element. Other times it says well, we'll just say with the word element right now. So element means one type of, or one substance that has the same atom type. So in this case, I could have a single titanium atom, and that's a element. Now the word element is like the word sheep. So just as I could say there are 5 sheep over there, or there are only 1 sheep, it's what's called a collective noun. You could have 4 particles here, and it's all considered an element. On the other hand, you could have 6.02 times 10 to the 23rd particles, but it's all considered the same element. So compound is the same way. You could have sodium chloride. You'll notice that NaCl, Na is one type of element, or atom type. Cl is another type of element, or atom type. And because they're different, then it's a compound. If you have one single particle, that's a compound. If you have multiple particles and they're all the um, same particles, then it's still considered a compound. Now, if you say compounds, then that means that you're referring to multiple compound structures, such as salt, table sugar, and water. The chemical symbols, which represent the atom type, was what we see here. And notice how we just slapped together two elements like this, and then voila, we have a compound. So ergo, H2O is considered a compound because they have different atom types, or two or more atom types. Another way of saying that is they have two or more elements. We have to rely on models because the molecules are so small that we just can't see them. Just to kind of put this into a frame of reference, there's my thumb. That thumb has roughly, if it was 3D, it'd be about 18 mils of water. It turns out that over this many molecules, I'm sorry, yeah, we got it. This many molecules of water can actually fit in 18 mils. That's how small they are. So that's why we have to make models, just because we don't have any instruments that can resolve that small a distance. All right. So we talked about the definition of compound. We got that down. Now we're going to get into something called molecules. And the best way to explain molecules is Dave and Buster's. So to use an analogy, if you go to Dave and Buster's at night, you're going to see a whole bunch of single people there, all playing games with their beers in their hand and an empty pocket or empty wallet. During the day, if you go to Dave and Buster's, you're going to see these cluster of people that we call families. So there's the happy kids, yay. There's the mom, boo. And Dave & Buster's is filled with these family units. Okay. Now, at night, you may have a bunch of buddies that are all hanging out, losing all their money, drinking their beer. And there's this social cohesiveness, but that social cohesiveness is nowhere near as strong as the family unit that you see there. Family units are obviously much stronger, have much more social cohesion than individual friends. Now, there are substances that mimic family units. The best example is going to be water. So here is the structure of water. I put dots on there representing electrons. Don't worry about those details. But bottom line is you see a hydrogen element, and an oxygen element. And they're all connected. The hydrogens are connected to the oxygen by special bonds. Instead of family bonds, we call these chemical bonds. So just as there's family bonds for family units, although some days are worse than others, there are chemical bonds that combine between atoms, and we call these molecules. So another name for these chemical bonds are chemical binding forces. So these chemical bonds are important. They really allow us to convert from one substance to another. And that's what really allows changes to pure substances. Now, the friends, they don't have those special family slash chemical bonds. Likewise, there are substances that although they're attracted to each other, they don't have those special chemical bonds. We call those forces in between physical binding forces. Now, it's possible for a water molecule to have both chemical and physical binding forces. So here is one water molecule. Here is another water molecule. In between the molecules, then it's physical binding forces, PBF. However, on the inside of the water particle, then we have chemical binding forces. Another word for chemical binding forces is chemical bonds. Now there is another term for physical binding forces between molecules, because whenever we have these chemical binding forces, the name of the particle is also known as a molecule. We call these intermolecular forces. So if I give you a nice representation on an atomic level of a water molecule or titanium, you should be able to indicate chemical and physical binding forces. Or I could give you a multiple choice question indicating chemical or binding forces. So this is when you have to look at it at an atom level or a molecular level. So for example, I could ask you, does this contain, or is this a molecule, yes or no? And you would say yes. And based on this structure right here, the minute you see that dash, then automatically it's going to be a molecule. Because only molecules have those special chemical bonds, in which we represent as a dash. On the other hand, if I were to give you something like this, here's 3 atoms of iron. Is this a molecule? And you would say no, because there's no chemical bonds you can see in between them. Now if I were to draw 2 of these molecules right there, now there's going to be in between physical binding forces in between the 2 molecules. Other questions I could ask on the left, is this a compound? And you would say no. And on the right, is this a compound? You would say no. On the left, notice they're the same atom type, so therefore it has to be an element. It's not a compound. Over here, same thing. They're all iron atoms. It's the same atom type. So yes, you can have a molecule and have it be an element. One of the most popular elemental molecules is oxygen, O2. It's made up of the same atom type, so it's an element, but there's chemical bonds in between, and that makes it a molecule. On the other hand, you could have something that looks like this, NaCl. It has physical binding forces in between, so it is not a molecule. On the other hand, it is a compound because it has different atom types, or 2 or more atom types. So this talks about the definition of molecules, so make sure you're able to identify and understand and reason out characteristics such as molecule, elements, and compounds. Now within molecules, oftentimes they have a different number of atoms that make up that molecule. So in this case, if there are 3 atoms that make up the molecule, we call it a triatomic molecule. So tri means 3. Ozone, O3, is also a triatomic molecule. Don't worry again about the dots. Only worry about the dashes and whether they're the same atom type or not. The bottom one that I just circled is an element, whereas the top one is a compound. So make sure you're familiar with diatomic, triatomic. These ones right here, these are all diatomic gas molecules. And it's hydrogen, nitrogen, gas molecule, oxygen, fluorine, chlorine. Yes, you want to know these. Notice they're all elements because they all have the same atom type, and this one's color coordinated. On the second to the last page of your syllabus, there's a nice saying, have no fear of ice cold beer. And this little mnemonic trick will help you memorize all of the diatomic gases, because you'll be seeing those quite a bit in future weeks. And so you automatically have to know that whenever you have these individual elements, they like to create these diatomic molecules, and they tend to be gases at room temperature. Now, some other things I briefly want to talk about. It's not directly on the slides, but we need a quick way of looking at a formula to figure out whether it's a molecule or not. So one little trick is if you see a formula like this, NaCl, and you're able to recognize that one of the elements is a metal, then automatically it is not going to be a molecule. So metal nonmetals or pure metals such as titanium, copper, they do not form molecules. We tend to refer to those as ionic formulas, as opposed to H2O, which is a pure nonmetals, and then these are considered molecular formulas. So now we're going to get into the next part where we talk about mixtures again, and then we'll get into some of these definitions: physical changes, chemical changes, physical properties, and chemical properties. So this is slide 12. Let's go ahead and pop this up again. At the beginning of this video, we talked about pure substances versus mixtures. A mixture is when you have more than one pure substance mixed together, such as water and pasta, although it's already written there, water and pasta. So that is a mixture. Now, there's some sort of physical method that we can separate it, where it has nothing to do with making or breaking chemical bonds. So you can use a strainer, for example, and that helps physically separate the water from the pasta. Or you can use another physical separation technique such as evaporation. We have two other definitions you need to know: homogeneous and heterogeneous. Now, just because you saw two things mixed together doesn't mean that you see two things. Maybe you only see one. So for example, if I were to sit there and look at some mixture of, let's see, ooh, what am I in the mood for? Oh, I know, milk. Here I have a nice glass of milk. There's the milk right there. It's red milk. And there's a person all the way down at the end of the hall. And there's a glass of milk on a table that he really wants. From this distance, even though we know that milk is made up of water, proteins, and other stuff in there, he can only see one thing. Because he can only see one visible component, then we call it a homogeneous mixture. So homogeneous means the same throughout. On the other hand, if he were to sit there and walk right up and get his eyeball, there's his eyeball right there, and look really, really close at the milk, he may start to see pieces of the milk curdling, little solid pieces floating around. He may see little particles inside. Ooh, that's nasty milk. The minute he sees two or more substances, then automatically it's heterogeneous mixture. So these definitions are all about what you can see, not what you know is present, but what you can see. So brass is actually a mixture of copper and zinc, and we can actually melt it to help separate it out. But all we can see is one thing, just that ugly color right there. So therefore it's homogeneous. On the other hand, if we were to sit there and mix together copper pennies and waters, regardless of what distance we're at, it's pretty easy to see the difference between the two. Then automatically it's heterogeneous. So it's some examples you can play with. Now we're going to get into those other definitions that I mentioned in the outline. We have physical binding forces and chemical binding forces. We talked about these earlier, just as a refresher. Some particles of a pure substance have both physical and chemical. So water molecules, they have chemical binding forces. And then between the molecules, those are going to be physical binding forces. Iron, on the other hand, only has physical binding forces. Now, by understanding physical and chemical binding forces, we can start getting into new definitions. Physical change and chemical change. Now, let's start with chemical change. Chemical changes are anything that make or break chemical bonds. They have to make or break chemical bonds. For example, if I wanted to do a chemical change on this water molecule, I would have to break apart the chemical bonds. So I'm drawing squiggly lines there showing how it's being broken, and I'd have to form new ones. So, because I'm making and breaking chemical bonds, this is called a chemical change. Now, here is one definition of a chemical, or here's one example of a chemical change, example. This is electrolysis. So by shooting electricity through water, we can create hydrogen gas and oxygen gas molecules. Another example is burning. So here is charcoal, represented as C. There's oxygen, and when I have a flame, I break the bonds and make new ones, creating carbon dioxide. So make sure you know one example, such as burning or electrolysis. Uh, Physical changes are changes to particles that do not affect chemical bonds. So any change that doesn't affect. So for example, here I have solid iron. I'm then going to heat it up, and now I heated it up so much that I turned iron into a gas. Now, based on our earlier pictures where you see dashes of whether their dashes are formed or not formed, indicating chemical bonds, there are no chemical bonds that have been made or broken in this example. So I went from a solid to a gas, heating it up. But this is considered a physical change because there was no bonds that were made or broken. So any type of melting, freezing, heating, heating to vaporization, all of that is physical changes, not chemical. So when you boil water, that's just a physical change because you're not breaking any bonds. So if I tear a piece of paper, although I'm separating it into different parts, I haven't broken any chemical bonds. And again, it really helps to know what's happening on a atomic level to understand this. Most of the time we just memorize whether a physical or chemical change occurs just out of habit because we've already learned what happens through other people's experiments. So make sure you have those down. You have an example for that. Another definition, physical property and chemical property. Physical property, completely different type of definition. It's all about the characteristics. So one characteristic of me is that I have brown-black hair. Another characteristic of me is that I'm short. Another characteristic of me is that I have big muscles in my dreams. These are all characteristics of me. A characteristic of water is that it's clear, is that it's tasteless, is that it's a liquid. So any characteristics, those are physical properties. So melting point, boiling point, those are all physical properties. Anything that involves physical changes are also considered physical properties. Now, chemical properties are known types of chemical changes. They're not ones we made up. They're ones that occur in nature or occur in a laboratory that we can actually do. And I've already given you one actual chemical property of water, and that's electrolysis, where we send electricity through the water, and the waters break up into hydrogen and oxygen. Technically, it's hydrogen gas and oxygen gas. So it does involve bond breaking and bond making. That's its chemical changes. Again, it has to be a known chemical change. It's not one that you could just magically make up. So make sure you have one of these memorized. Charcoal burns is a chemical property, that it can burn as a chemical property. Because we know that carbon of charcoal mixed with oxygen forms carbon dioxide, and the bonds in the oxygen are broken, and then new ones are formed around carbon, creating carbon dioxide. Iron rusts, that's another example of a chemical property. Alright, so we talked about elements, which is gold, carbon, aluminum, for example, and then we also had you memorize element symbols. And the symbols make it easier to manage these elements when we're reasoning out chemical concepts or chemical reactions. So the chemical symbol for gold is Au, carbon is C, aluminum is Al. You can have one letter symbols, and they all have to be capitalized. Two letter symbols, the first letter is always capitalized, the second one is not. So if you wrote cobalt like this, then it's completely wrong. Why is that? Well, let's reason this out. If you wrote something like this, CO, then you're saying that the capital letter C is carbon, capital letter O is oxygen. So this is carbon monoxide. This is the stuff that kills you if you are in a closed off room and your car is going on, or closed off garage and a car is going on. So that's a big difference from CO, lowercase o, because then that means that's the element cobalt. So make sure you have your capitalization properly. Now as far as the name capitalization goes, that's optional. So you can have a lowercase c on copper or an uppercase C on copper. But where it's crucial is the element symbols. Now, you'll notice that some of them are pretty straightforward, C and F and O. Other ones are not straightforward, like CU instead of CO. The reason for that is we ran out of letters. We couldn't say CO for copper because it's already been taken by cobalt. So people started looking at the Latin form of it, of the element. So the Latin name for copper is cuprum. So that's where they got the U from Cu. The Latin name for sodium is natrium. And that's where they got the Na for sodium. So you've gone through these already. Let's start going into more details. Here is the periodic table. The periodic table is organized into periods and groups. So periods are just rows. So for example, for the first quiz, you had to memorize the first 3 rows, aka the first 3 periods of the periodic table. Going down the columns, this is a group. So 1, 2, and then over here is group 3A and 4A and so forth. The periodic table is designed in that groups are clustered together in the same group because they share similar properties. So the ion for beryllium is a 2+, the ion for magnesium is a 2+, because they're both 2 pluses, then they're in group 2. And we also have common names for these groups. So what's an ion? Don't worry about it, we'll get into that later. Just memorize the positive charges or negative charges for the ions we had to memorize, but we'll get into what they mean later on. Now, there's something called repeated properties. Repeated properties, the term for repeated properties is periodic. So just to give you an example of the term periodic in motion, this is a clock, and you'll notice that it goes from 12 to 1 all the way around back to 12 because it's constantly repeating over and over and over, then it's periodic. It turns out that these groups all have very similar properties. So, as we start counting from the lowest to highest, we start repeating the properties. So for example, hydrogen has a positive 1 charge, or 1+. And then as I start counting across to the third element right here, lithium also has a 1+ charge. So you'll see that the property of charge repeated itself. Because it repeated itself, that's where we get the term periodic. Now you have to memorize all of these. These are the Same ones that you had to memorize uh, that was talked about in previous material and your study handouts. So it's nothing new that you have to memorize. I just kind of repeated myself. All right. So that concludes this set of slides.